Okay, so what we were doing last time is we started with roses. And so what has changed is now we have a cosine n theta. So you remember if it's n theta like that, so if it's cosine 2 theta or 3 theta, it modifies the period. So instead of the period going from 0 to 2 pi, now you have a modified period, right? So let's say from 0 to pi. So that means you can fit in an additional cycle or 2 cycles or 3 cycles. Why does that even affect us? Well, if what we're doing is looking at the distance from the x-axis, then you see how going away and close and away and close and away and close, this happens to repeat more times, right? Okay, so we have 4 cosine 2 theta, and we put in our values here. So why don't we plot those? So at 0, we're at 4. At pi over 2. And you know what? Okay. So at pi over 2, which is here, we are at -4. At pi, we're at 4. And then at 3 pi over 2, -4. 2 pi, 4. Okay, so do you see what happens there? Like this, right? Okay, so what's happening? It's far away, and then at the x-axis at 0, and then it's far away again, and then back on the x-axis, and so on and so forth. So now if we're going to translate this over to our polar axis, what's going to happen? Here, it's at its maximum radius. Here, r is 0, right? So it's at the pole. What's the value there? When is this thing 0? It's right in between 0 and pi over 2, right? So where is that? Where it hits 0 at pi over 4. Okay, so take a look here. Where is pi over 4 here? So it hits 0 right around pi over 4. And then where else does it hit 0? At 3 pi over 4. So right here at 3 pi over 4, it hits 0. Okay. At pi over 4, it hits 0. And then where else does it hit 0? Right here between 7 pi at 5 pi over 4, r is 0. And then here at 7 pi over 4, r is 0. Okay? So take a look at what's going to happen now. So let's graph it here. When theta is 0, r is 0. When theta is 0, r is 4. So 2. You know what I want to do? I want to do 1, 2, 3, 4 here. Okay? So when theta is 0, 4 is here. Right? And then what happens? Where is it at pi over 6? 2. So where is pi over 4? Pi over 4 is here in the middle. At pi over 4, this thing hits 0. Okay? Is that right? Yeah. So, and then at pi over 3, where is it? It's -2. So where would it be? Not here, but on the opposite side here. So far, what have I graphed? This. Is that right? Okay. So now, so at pi over 2, it's at -2. -4. Right there. Okay. At 2 pi over 3, it's negative 2 right here. And then in the middle here, look, it goes from negative to positive. So right in the center at 3 pi over 4, it hits 0. 3 pi over 4 is here. It hits 0. So now look at what I've graphed. I've come here, here, and here. You see that? Yeah. And then at 5 pi over 6, what is it? 2. And then at pi, what is it? 4. And then at 7 pi over 6, it's 2. And then at 5 pi over 4, which is here, how much is it? 0. So now where did we go? Here, 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 here. Right? Oh my gosh, I know. Like, look at that. Like, look at how amazing this is. So now we're at 5 pi over 4. Okay, 4 pi over 3, what is it? Negative 2. So look, we're up on the opposite side here, 4 pi over 3. 3 pi over 2, it's negative 4, so all the way up here. Oh my God, I love this stuff. 5 pi over 3, it's negative 2, so here. Okay, and then right at 7 pi over 4, here, 7 pi over 4, what is it? 0. So now what have we graphed? So from here we go up here, up, here, and here. Okay? And then where are we at? At 11 pi over 6, how much is it? 2. And then at 2 pi, 4. So back down here, over, and look at that. That's the rose. Do you see that? How many petals does the rose have? 4 petals. So do you see how, like, over from 0 to 2 pi, it traverses like in and out that shape, right? So I want to highlight, right? I want to highlight this like oscillation of the distance, right? So we start at the maximum, gets to 0. Then it goes to maximum to 0. Maximum to 0. Maximum to 0. Okay? So I'm talking about maximum radius. Radius is always a positive value, right? It's the absolute value. So here, radius is a maximum, then 0, maximum, 0, maximum, 0, maximum, 0. Isn't that beautiful? It's a beautiful, beautiful thing. So what happened here is we had 2 theta. That's an even number here. So you have twice the number of petals, 4. And then you'll see later why, if it's 3 theta, you only get 3 petals. You'll see how that works. It's like such a beautiful, amazing thing. All right, so that is your rose. Okay, all right. So, okay, roses, these are the types of roses you can have. I just want to highlight a couple of things because later on when we get to symmetry, all of this thing will fall like better into place. So here we just graphed A cosine n theta, all right? And look, when you have like 4 petals, when you have n equals 4, you've got 8 petals, and this is how it looks. When you've got n equals 5, this is how it looks. What's the one thing that's the same between the two of these? This first one is centered around the what? The polar axis. Right? That's the one thing, and that's characteristic of the cosine. You'll see that later when we're doing symmetry. Okay? Hang on. When we have sine, right? When we have sine, look at how it looks. There is no petal on the polar axis. Okay, so for the sine, no petals on polar axis. So basically, when you're walking down the street and you see the graph of a rose, that's how you can tell if it's a sine or a cosine rose. Okay? And okay, so this distance here, the length of a petal, that's the radius, and that's the same as A. And that's the A here. Okay? So that's the same as the R. Okay? Yes.
So the graph that we got was cosine one. So even though the examples in the box has only 4 and 5, we can always go to 2 and 3 as well. So like n equals 2 and as well.
Yeah. As long as n is greater than 2. 2 or greater. Because if n is 1, then it's a circle. Okay. Yeah.
So when they ask,
Let's take a look at some of these animations. All right. I've got another one here for roses. Yes. Okay. So, let's do b cosine theta. All right. So here we go. We just graphed 4 cosine 2 theta. So I've modified my notes to match these ones so that, you know, we could have a visual. All right. So here it is. This is exactly what we graphed, right? From 0 to 2 pi, it was 2 cycles because it's 2 theta, so it was 2 cycles. And so let's take a look. You ready? Here we go. There, it's 0 right now. You see that? Negative, negative, right? This is where it was supposed to be like here, pi over 2. It's a negative radius, or a negative A. All right, then moving on. Here we go. Back to 0, right? And then goes out. And then back to 0. Back out. 0. And then finally, it completes the curve. All right? It's so beautiful. So let's take a look more at B and N. Okay? So here is 4 cosine 2 theta. All right? And what if I have okay, so look, here is 3 theta, right? It's still a cosine, right? And then here, 4, right? We've got 1, 2, 3, 4, 5, 6, 7, 8 petals. And then 5, 6, 7. So do you see what happens?
if it's like 2 theta, then
This is the highest it could go, huh?
if it's like 4 theta, then it's
8 petals. If it's even, double. If it's odd, the same. All right? So now, let's go back to 2 theta. This is what we had. And now, this is the B. So here's what happens when the radius gets bigger.
Oh, I love that.
When B gets bigger and when it gets smaller. Oops, 0. All right? So
So B can't be a integer?
B is an integer.
B can't be a,
I mean, it can. This is just how this was set up.
what would it look like if it was like 1.0?
Same, it'll just be 1.4 units long. It'll just go like in
What if,
between.
if the thing that determines whether or not it's even or odd.
It's the same. Okay, so take a look at this. N wouldn't be. N is an integer. It's specified.
But like in calculus, there's never a time when.
No, because it's in the theorem, like in the definition, it's specified. If you look in that box,
No, I saw.
N is an integer. Okay, so look at this one. Here we have A cosine 1 theta or A sine 1 theta, and that's a circle. All right? So now, when this gets larger, now you're increasing the cycles within a period, right? Because you're changing the period. So when n gets larger, now it's 2 theta. And now look, this is the cosine in the blue and the sine. Okay, so you see how their symmetry is different. And then 3, 4, 5, and so on. All right? Yeah. We will
Is one cycle, right?
huh?
Like this, each petal is one.
It's no. Each petal is not 1 period. It's just like from 0 to pi over 2 for the cosine. And okay, so this will give us a better idea. So take a look at this. Here we have cosine. So look at what's happening, right? This is half a petal until pi over 2. Now we're at pi. I'm sorry, now we're at pi over 2. Now we're at pi, 3 pi over 2, and finally 2 pi, right? Okay, now, hang on. Huh?
Why aren't the points like actually on like pi over 2 and like pi?
What do you mean?
They don't like align.
On the graph.
On the graph, right? On the right.
On the,
The green
They
points
do.
aren't on the lines.
what do you mean?
They're like a little bit off the line.
Are they?
Yeah, like half of them are in a line.
I'm not really.
It's okay.
It's just to show us.
Okay, so here, okay. So now, oh, you know, this should say 3x. Okay, so that should say 3x. So now what happened is, okay, so that was 2 theta, and we had twice the number of petals because you saw like for each one, you know, like from 0 to, you know, pi over 4, it was half, and then pi over 2, and so on and so forth, right? Now I have 3. How many petals? This is going to have 3 petals, the same number. So why is it that an odd number gives you the same number of petals, but an even gives you twice the number? So take a look at what happens. Look at how it traverses the curve. Okay, so we're going, and look at this. Look at here, and right there. Okay, so look, where are we right now? We're still at pi. So what happened when it was 2 theta, right? It wasn't finished drawing it until we got to 2 pi. But when it's 3 theta, it finishes the rows at pi, and then the remaining pi to 2 pi, it just repeats over again. Do you see that? Yeah. So that's why when it's an odd number here, when it's an odd n, like 3x, 5x, 7x, the rows will have been drawn from 0 to pi, and then pi to 2 pi, it just retraces it. Okay? It doesn't draw new petals. Yes. Okay. So we're going to do the lemniscates. The lemniscates have the equation of the form r squared equals a squared cosine 2 theta. And they produce lemniscates which have an infinity shape. Okay. So the first thing we're going to do is r squared is equal to 16 sine theta. 16 sine 2 theta. Okay. So for the first one here, I'm going to plug in theta equals 0, right? So take a look at what I have. If r squared is equal to that, in here I want my r value, right? What is r? It's the square root of 16 sine 0, right? I just plugged it in. Yeah. These are all in radian because it's pi over 3. So that's going to be r equals 0. Okay? Now, here, when I take a square root of this, right? When I take a square root of this, what is, okay, so now that one was 0, so I didn't really do that. But what is r really? It's plus or minus the square root of 16 sine pi over 3. Okay, so it's 2 theta. 2 times pi over 6 is pi over 3, right? But it's plus or minus, and when you plug it in your calculator, you get plus or minus 3.7. Okay? And I'm just going to make a little mark here that this is our pi over 4. And now when I put in the pi over 3, it's plus or minus the square root of 16 sine 2 pi over 3. And when I put it in the calculator, wouldn't you know it? It's the same value because at the pi over 3, sine have the same value. Yeah. Yeah.
Homework?
Uh-huh.
You want charts?
Yes. Okay, let's ask those questions later.
That's why I was hesitant to ask,
Yeah.
because it's like one of those.
Okay. No, we're not. Okay. So here we have plus or minus the square root of 16 sine 2 times pi over 2 is pi, and that's 0. Okay. And now here, what do we have? This is the important part. Plus or minus the square root of 16 sine, how much do I get? It's 2 times 2 pi over 3. 4 pi over 3. Okay. Now, okay. This is my favorite. Okay, this is my favorite part. What's sine of 4 pi over 3? Oh. What's sine of 4 pi over 3? Yeah. Okay, so here we go. We're back. So here, sine of 4 pi over 3 is a negative value, and we can't take the square root of a negative number, so this is undefined. It's non-real. You can't graph it.
So is the next.
So for the entire time that sine of theta, right? So if you go in the unit circle, sine is positive here from 0 to pi, but then from pi to 2 pi, sine is negative. So for the entire duration that inside this root you get sine of something pi to 2 pi, it's going to be undefined. So for example, here it's going to be sine of 10 pi over 6, which is 5 pi over 3, so that's undefined. Sine of, how much is this? 2 pi, that's 0. Okay? And then here when we get 7 pi over 6, now it's going to be 7 pi over 3. It's back in the upper quadrant, so we get this, because it's 2 theta. The equation is 2 theta. So here we're going to get 16 sine 7 pi over 3, and that's cool. We're still going to get 3.7 plus or minus. Here is where it's pi over 4. When you plug in 4 pi over 3, you get 2 pi over 3. So again, it's plus or minus 3.7. Okay, what about here? Here we're going to get plus or minus 16 sine 3 pi. That's 0. These will give us undefined again. And then finally 0. Yeah. Okay. So you're seeing now, sine and cosine, we always knew that it was, these were periodic functions, which means they repeat after, a cycle. So here too, that's periodic. It's going to keep repeating. Okay. Now, when is the radius going to be a maximum? So let's think about this for a minute. This is a sine curve, right? When does sine hit its maximum value of 1? At theta equals what? Pi over 2, right? Yes? Okay.
Oh,
Sine, right? Okay. So, right, but now it's 2 theta. So look, because it's 2 theta, when theta is pi over 4, right? What do we get here? Plus or minus 16 sine 2 times pi over 4. What is that? 16 sine pi over 2. That's the maximum, right? So we get a maximum value of 4. So that's where theta is max. Okay? So here, maximum theta of 4. Maximum theta of 4, or plus or minus 4. Okay, when theta is 0, r is 0. When theta is pi over 6, we are at 1, 2, 3.7 and negative 3.7. Okay, when theta is pi over 4, we are at 4, and -4. When theta is pi over 3, we are at positive 3.7 and negative 3.7. And then where are we? At pi over 2, 0. So what have I done? What have I done? I have done boom, 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 boom. Okay? Do you see that? Should we? Okay, so look again. Look up here and let me trace it again. From here, maximum, minimum, maximum, minimum. Okay? So where is this lemniscate complete? Right here. And then from pi to 2 pi, it retraces itself. Okay? Okay, so spirals of Archimedes, these are polar equations that have the form r equals theta plus b. Okay, let's think about this for a minute. So suppose b, okay, so a is a number, b is a number. Okay, and if b is a number, we could just make b equal to 0 for our purposes, right? So, for example, r equals, oh, I don't know, 2 theta. Okay? All right. There is no sine, there is no cosine. Okay? This is just like a linear equation. It's just like y equals 2x, right? So, what happens as theta increases? What will happen to the value of r? R also increases linearly, right? If theta doubles, r doubles. If theta triples, r triples, and so on and so forth. So suppose we're graphing now r equals 3 theta. Okay, let's just get a feel of what is it that we're doing here. When theta is 0, r is 0. When theta is pi over 6, this is just 3 times pi over 6, right? Which is how much? Pi over 2, which is 1.57, right? If pi is 3.14, half of that is 1.57. So we're just going to say 1.6, okay? There is no sine, there is no cosine, it's just pi, 180, or 3.14 divided by that. And then at pi over 3, 3 times pi over 3, this is just pi, or 3.14, okay? And similarly, if we just keep doing that, 4.7, 6.3, 7.4, 9.4, okay? I'm just going to stop there because I don't even have enough space. So what I'm going to do here is again calibrate this 2, 4, 6, 8. So now look at what happens. Okay? When theta is 0, r is 0. When theta is pi over 6, it's 1.6. Pi over 3, 3.1. Right? So look at what happened here. Pi over 2, 4.7. 4.7. 2 pi over 3, 6.3. 5 pi over 6, 7.4. And then pi, it's like 9 point something. So what's happening? As you're moving further and further out, right? Theta is just getting longer, longer, longer. I'm sorry, radius is just getting longer, longer, longer. But now when you connect all of these, what have you made? A spiral, okay? And that spiral will just keep going out and out and out and out and out, okay? What if you were to graph theta plus 2? What's happened there? Theta plus 2, yes, Elliot. It just moves over, so it starts here, right, at 2, and then it'll just like keep spiraling from there. You see what I mean? And if it's like negative, then it'll like spiral from the other way. But always that way, huh? No, we're not going to go there. That's just, huh? Bernoulli is another scientist. Okay, so we can use symmetry to reduce the number of points you need to sketch something. When you first started sketching parabolas, you would like do like all these weird points, and then you realized, oh my God, if I only put 2 points to the left of the axis of symmetry or to the right of the axis of symmetry, I could just mirror them and I've got my parabola, right? It reduced your work literally by a half. Same thing here. We could use symmetry in order to, instead of graphing from 0 to 2 pi, I could just graph from 0 to pi and then mimic those points. So let's take a look at some symmetry and then I'll take questions. Graphs of polar equations can be symmetric with respect to the line pi over 2, theta equals pi over 2, the polar axis, or the pole. So take a look at this one. This graph here has symmetry with respect to theta equals pi over 2. Okay, so you see how it's symmetric along that vertical line? This one here is symmetric with respect to the polar axis. It's got that vertical symmetry. This one is symmetric with respect to the pole, right? It's just like being symmetric with respect to the origin or the x-axis or the y-axis. Okay. So remember with functions, with rectangular functions, there was a test like we would do, okay, x-axis, y-axis, origin. And then remember what we did is for the x-axis, we replaced y with negative y. You remember? X with negative x, and see if like you get the original function back. Same thing here. But this is the test for symmetry. So if you want to test for symmetry with respect to the polar axis, you plug in negative theta for theta and see if you get the same function back. Theta equals pi over 2, negative r, negative theta, and the pole r to negative r. Okay? And then here is some like a hint. If an equation is symmetric with respect to theta equals pi over 2, it's enough to graph from like negative pi over 2 to pi over 2. So I've put this here, but I'm going to tell you to not memorize this. It's not worth it because once you understand what's going on, you will do it instinctively anyway. So don't memorize this. But, okay, this one. Let's see if you can make sense of these so you don't have to do as much memorizing. The pole is the easiest. If something is symmetric with respect to the pole, like this lemniscate, do you see how whether you have positive r or negative r, it's the same, right? If something is symmetric with respect to the polar axis, right, the polar axis, look, whether you have positive pi over 3 or negative pi over 3, your r's are the same value, right? And then here, if you have negative r, you're here, but then if you make it negative theta, then you're back there, right? So you have to do negative r and negative theta. So in the beginning, just refer to this chart and then it'll be like, you will see the idea. Here is you've seen all of these before. I was like cutting it up and putting it on your pages until now. This just puts it all in one page, okay? For your reference. It's cute. Yeah. Maximum R values and zeros. Okay, so how do you find maximum R values? The maximum R value is radially the furthest point on a graph. Okay? How do you find this? Find the theta values for which R is maximized. Okay? So, if it's a sine function, ask yourself, for what theta is sine maximum? Pi over 2, 3 pi over 2. When is cosine maximum? 0 and pi. So, okay, so to find maximum R values and their locations, you're going to do just that. Determine the values of theta where you have maximum values. So, for example, Sine is plus or minus 1 at pi over 2 and 3 pi over 2, what we just talked about. Okay, so that's the location, right? This is the location. And then for the actual R value, evaluate the function. So you want R equals here. Okay? The location is theta. Okay? So just like where is this a maximum at x equals 2, what is the maximum value? Y equals 24. It's the same thing here. Okay, what about zeros? The zeros are where the radius is 0. So these are the same points where the function would cross the x-axis in the Cartesian coordinate plane. So how do we find zeros? Set the function equal to 0 and solve for theta. So look, suppose you have this equation and it says find the zeros of this. Chapter 4 all over again, 4.3. Oh no, was it 5.3? Okay. So you say 1 minus 2 cosine theta is equal to 0. And then you subtract 1, divide by 2. So 1 over 2 is equal to negative cosine theta, right? No, positive cosine theta. So what's theta? Where is cosine equal to 1/2? Pi over pi over 3 and one more, 5 pi over 3. So it's at pi over 3, 2 pi over 3 it's not, 4 pi over 3 it's not, but 5 pi over 3 it is. Okay. All right, let's actually do one. Okay. Identify the type of curve given by this. So let's just do that. What type of curve is it? I have a rose. What do you guys think? Yes. Okay, so this is a rose. Thank you. Rose with 3 petals. Good. So now it says determine the symmetry, zeros, and maximum R values. Okay, so let's talk about symmetry. We're going to go to that chart here. We're going to check polar axis, theta equals pi over 2, and pole. So for polar axis, right, what do? We switch theta with negative theta. So let's see if we're going to get the same function. R equals 2 cosine 3 negative theta, right? That means R equals 2 cosine negative 3 theta. What's cosine of negative theta? Yeah.
No, it's positive. It's positive. It was the even odd from chapter 5.
It's the even odd from chapter 5. So, sine of negative theta is equal to negative sine theta. Cosine of negative theta is equal to cosine of theta, because cosine is an even function and the negative theta. So this is R equals 2 cosine 3 theta. Did I get the same function back? I did. So it's symmetric with respect to polar axis. Once you do that, you don't have to continue anymore. Okay? Yeah, no, because it's not going to be symmetric to more than one thing. So once you get the one, just stop. Okay, let's do zeros. Yes. You do it. No, you test it until you get one that works. Yeah. Well, if that doesn't work, then you go to the next one. Yeah. So to set it equal to 0, to find the zeros, we have to set this equal to 0. So cosine of 3 theta is equal to 0. Where is cosine 0?
Pi, 0 and
Okay, so it's when the angle is equal to 0,
2 pi.
pi over 2, right? Cosine is 0. At 0, pi over 2, I'm sorry, pi over 2, pi over 2, 3 pi over 2, 5 pi over 2. You have to keep going. Okay, so what are we going to do at this point? We have to divide and divide, right? So you have to keep going until you get 2 pi in the end. All right, so take a look. 5 pi over 2, 7 pi over 2, 9 pi over 2, 11 pi over 2. Why am I doing this many? Because now theta is equal to, you divide by 3, pi over 6, 3 pi over 6, which is pi over 2, 5 pi over 6, 7 pi over 6, 9 pi over 6, which is 3 pi over 2, and then 11 pi over 6. So you have to get all the possibilities from 0 to 2 pi. Okay, and I have to stop here today.